Hello, let us look at some questions regarding parallelograms first. So here we have TYUI is a parallelogram with this information. What is the perimeter? So now, if I were to have a parallelogram, I'm going to assume that this is the one. And I'll say this is TYUI. And then saying that TY is equal to 6. And then YU is equal to 8. What is the perimeter of this parallelogram? In fact, it would be simply, we know that opposite sides are equal to each other. So since this is 6, this must be 6 as well. Since this is 8, this must be 8 as well. So therefore, the perimeter is, in fact, 6 plus 8 plus 6 plus 8, which becomes 28. Now, how about part B? Do we have enough information to find the area? In order for us to find the area, I need to know the height. But the thing is, as you can see, this parallelogram can be this way, or it could have been this way. I guess it's kind of hard to see, but it can be a little bit slanted down or up. So we have no idea. So therefore, since a height is not fixed, we don't have enough information to find the area. All right, let's look at the second question here. WXYZ is a parallelogram. So we have a parallelogram here. WX Y, Z is a parallelogram. They want us to prove that W is in fact congruent to Y. One of the property states that opposite angles are congruent, so that's one way, given that this is a parallelogram. But if I don't use that, for example, if I were to only use the definition of a parallelogram, meaning opposite sides are parallel, what I could have done was, as you have discussed in class, just draw a diagonal and then state that, hey, this is a reflexive. And this angle is congruent to this angle because we realize these two sides are parallel and alternate interior angles are congruent. And then secondly, we can say this angle is congruent to this angle by alternate interior angles between these two sides. So we can say angle side angle. We can say triangle X, Y, Z is congruent to triangle Z, W, X by angle side. Then we realize that angle W must be congruent to angle Y by CP, CT, C. All right. Let's look at number 3. In a quadrilateral, WORK, and I'm going to intentionally make a quadrilateral that doesn't look like a parallelogram. Just randomly making something. And then, but one thing actually that we get to realize is WO is parallel to RK. So let us say this is parallel to this one. So WO, RK. They're parallel. And then WO is in fact equal to RK. So this side is equal to this side. So we have one pair of opposite sides that is parallel and congruent as well. Then how can we show that WORK is a parallelogram? So what we have to do is this. If I were to draw a diagonal between K and O, then we get to realize that, hey, this is reflexive. And since these two lines are parallel, as you can see, this angle must be congruent to this angle, which states that upper triangle the blue triangle that we have is congruent to the lower triangle by side, angle, side. So we can simply say that triangle angle RKO is congruent to angle WOK because alternate interior angles are congruent in parallel lines, which was mentioned over here. And then KO is congruent to KO. So we now realize that triangle, by reflexive of course, but triangle RKO is congruent to triangle WOK by side, angle, side. Then we realize that this side must be congruent to this side as well by CP/CTC. So RO is in fact equal to WK as well by CP/CTC. Then, since two pairs of opposite sides are congruent, we know that it must be a parallelogram. So then WORK is a parallelogram, which is one of the ways which we discussed in class by having two pairs of opposite sides are congruent, because opposite sides are congruent. That's what we can write. Let's go for number 4. Use a clever dissection of the parallelogram to turn it into rectangle, and then prove that the area of parallelogram is its base times height. So we know that base times height is the area formula for rectangle. So then, basically what we can do is, imagine this is the parallelogram that which we are looking at. And then, what I'm trying to do is, I'm going to draw the height from that vertex over here. Then, after that, what I'll be doing is I'll be copying this triangle, bring it over right over here. Then you can see that this yellow one must be a rectangle, because originally we assumed that this is the right angle. That means this one must be right angle as well. And then since opposite sides are parallel, then we know that not only this angle is right angle, then this angle is right angle, because supplementary of the right angle must be right angle. And we can see that how opposite angles are all congruent because it's a parallelogram. Then we realize that yellow one must be a rectangle. Now, so that's basically what they mean by turning a parallelogram into the rectangle, which we have done. And how do you find the area of the rectangle? So this is height. And let's say this entire thing is the base. Let me call this one as B, and then let me call this one as A. Then A plus B must be our base. But the thing is, area of the yellow rectangle is the same thing as area of the parallelogram, because we found the yellow rectangle by cutting the piece off out of the parallelogram. So therefore, then A plus B times the height must be area of the rectangle, which is also equal to area of parallelogram. But the thing is, what is A plus B? Since this A is same thing as this A plus B essentially becomes the entire base of the parallelogram. So that's why we can say, even for the area of the parallelogram is base times height, just like a rectangle. All right, let's move on for the next question. Number 5, is it possible for a parallelogram to have, so let's look at the parallelogram first. E, N, T, U. En to be 4 and EU to be 12. Okay? N for size EU and NT to be 5 units apart. 5 units apart, that simply means when I draw this line, that must be 5 units apart. Now, is this possible? The answer is no, it's not possible. Why not? Because if you have to focus on the triangle that you see over here, we realize that this is a right triangle where hypotenuse should be the longest side, but in fact we realize that the leg is up longer than hypotenuse, which is not possible. So therefore, this is not possible. The answer is no. Number 6. In this exercise, let's try to look at extend. We have to draw the trapezoid. So intentionally, I'm going to draw. Oops. Draw trapezoid in this manner. Okay. Now, if I call this one as A, B, C, D, what they are saying is extend AB past B, so towards this way, to A prime such that B, A prime is same thing as CD. So it simply means I'm going to copy CD. And attach it right over here. Now, so I'm going to call this one as D prime, or A prime rather. And then extend DC past C to D prime such that CD prime, which is this portion, has to be equal to AB. So what I'm going to do is I'm going to copy AB and then put it over here. Now, then we realize that the endpoint must be D prime. Now, then we are now ready to close. The question is, prove that A prime, D is a parallelogram. How do you prove that this is a parallelogram? So, since this must be a trapezoid, we get to realize that this side is parallel to this side. Because one pair has to be parallel. But since these are extensions, so therefore we get to realize that extensions of parallel sides must be parallel as well. So this is parallel to this one. So we realize that two sides are parallel. Now, second, we realize that this line segment is equal to this, and this one is equal to that one. So if I were to call the smaller line segment as A and bigger one as B, then this is B and A. Since opposite sides are equal in length, A prime, which is equal to D prime, by addition postulate, I guess we can say that, and A prime is parallel to D prime. Since opposite sides are congruent and parallel, A prime, D must be a parallelogram. All right, that's how we can say A. How about B? Find the area of the parallelogram, and then ABCD, which is a smaller one. Find the relationship between those two. Now notice that the parallelogram that we are about to see is in fact made out of two trapezoids, and I'll show you here right now as well. We have the yellow trapezoid, and then what we can do is we can switch it up, and it fits the other trapezoid as well. So we realize that the area of the trapezoid is the half of the area of the parallelogram in this case. Now, then we get to see, oops, A, B, C, D. Two of those must be equal to A prime, D prime, D. That becomes our relationship. And how do you find the area ABCD? Since we mentioned that this parallelogram, area of the parallelogram is base times height, so we realize that this is height. Then area of the parallelogram is equal to base, which is CD plus CD prime, base times height, which is H. But what is CD prime? That's the same thing as AB, so we get to realize CD plus AB times H. That will be the area of the parallelogram. That tells us that area of the trapezoid is half of that. So we get half of H times CD plus AB. That becomes our final answer for part B. Let's go for part C. Let M and N and M prime be the midpoint of those things. So let me just say that, okay. So the blue one must be the midpoint, let us say. And then what we are trying to look for, this is M and M prime. And prove that M prime, which is this line segment, is in fact equal to AB plus CD. So now, so here, what we can do is this. Let me try to highlight the triangle that which we are looking at, which is, the parallelogram that which we are looking at. This. The blue one, if you can prove that blue one is a parallelogram, then we get to see that opposite sides are equal to each other. How can this be a parallelogram? We get to realize that first, this MD is equal to M prime D prime. Why is that? Because both of them are half of the congruent side, which is AD and then A prime D prime. So halves of congruent side are congruent. That's why part C tells us that MD is in fact equal to M prime and D prime. Now, but these are also parallel as well. Why? Because when opposite sides are parallel, their segments must be parallel as well. So we get to realize that MD must be parallel to M prime D prime. Those two line segments must be parallel. Then since one pair of opposite sides are congruent and parallel, this one is good enough reasoning for us to say that M prime, D prime, D must be a parallelogram. Soon as we realize that it's a parallelogram, then that tells us that M prime must be equal to D d prime. But dd prime is equal to cd plus cd prime, where cd prime is equal to cd plus ab. So that's how we can say m prime is in fact equal to ab plus cd. Now, so we did our first portion. Second portion, why is it that mn, which means this portion, is the half of m prime? Notice that m prime actually goes through two congruent trapezoid. Now, then, one thing that which we get to realize is that since m is the point where it divides first trapezoid to second trapezoid, the length must be cut in halves, about m. So then, that's why we get to realize that since mn plus m prime is equal to m prime, but since these are equal to each other, we get to realize that 2 times mn must be equal to m prime. And then when you divide by 2, then we get m must be equal to m prime divided by 2. That's basically what we end up getting. All right. But the thing is, at the end, to conclude that AB plus CD divided by 2, since we earlier we mentioned that m prime is essentially equal to CD plus AB, so then this is equal to AB plus CD divide the entire thing by 2. That's what we end up getting. All right, let's look at number 8.3.7. The diagonals of convex quadrilateral ABCD meets at E. So that means, so I'm going to have some sort of quadrilateral. Now, and then diagonals meet up at E. So here we have diagonals meeting up at E. All right, prove the centers of the circumcircles. How do you find the centers of the circumcircles? That means by the perpendicular bisectors. So then, what if I assume the perpendicular bisectors of this line segment must be somewhere around here? And the next, and then perpendicular bisector of these two becomes this way. This one is a little bit lower. Lastly, then we are looking at the green one must be a parallelogram. How do you know that? So first, what we can do is this: we can see that the blue lines must be perpendicular bisectors. So then here, this can be my right angle, perpendicular makes right angle, and here can be perpendicular right angle as well. Then you can see that angle 1 and angle 2 are congruent by alternate interior angle. They are congruent angles because they are right angles, and they happen to be alternate interior angles as well. Then angle 1 is congruent to angle 2 because they are right angles. But since 1 and 2 are alternate interior angles, then we get to realize that line L, M must be parallel. line L is parallel to line M because when alternate interior angles are congruent, L must be parallel to M. Same idea can apply for here. This can be right angle and this can be right angle. So then I can say A and B must be parallel by the same reasoning as the earlier one. Alternate interior angles congruent, then those two lines must be parallel. Since opposite sides are parallel, the figure must be a parallelogram. All right, so that's it. I'll see you later in rhombus and rectangles and also squares as well.